A credential can prove a specific fact, like age, nationality, or membership, without exposing the full identity record behind it. zk-friendly schemes make this practical, so holders reveal only what a verifier truly needs. So far, we've covered digital identity, verifiable credentials, public key signatures, and the intuition behind zero-knowledge proofs. Now we'll connect those pieces to credential formats that support selective disclosure and private verification. A basic signed credential provides strong integrity but limited privacy. A verifier can confirm that the issuer signed the document, but verification often requires seeing every field inside it. If someone only needs to know over 18, they may still receive a name, birth date, address, ID number, and membership status. That breaks data minimization. A normal document signature proves the credential was not changed, but it does not help the holder reveal only what is necessary. Selective disclosure changes the interaction from showing an entire credential to proving only the facts needed. If a verifier asks, "Are you over 21?" the holder should not have to reveal a name, address, or full birth date. Instead, they reveal that one claim, along with cryptographic proof that a trusted issuer signed it. The challenge is preserving issuer trust while keeping unnecessary data hidden. These schemes sit along a capability curve. SD-JWT VC is practical and web-friendly. It hides claims with salted hashes and reveals only selected values. BBS Plus goes further by letting holders prove chosen signed messages without exposing the rest. CL signatures and AnonCreds are designed for anonymous credentials, including predicates like over 18. zk-SNARKs can express very complex proofs, but they add setup, tooling, and operational complexity. The right choice depends on the proof requirements and the engineering trade-offs a system can tolerate. A credential scheme becomes zk-friendly when each attribute can be proven selectively. A holder might reveal a city, prove they are over 21, and hide the exact birth date and name. The signature must also support proof of possession without exposing the signature itself. At the same time, the verifier still needs confidence in the issuer behind the proof. If the process is slow or non-standard, adoption in real web and mobile environments becomes difficult. A BBS Plus credential works like one signature over several separate facts, rather than one indivisible document. The issuer signs the full set once. Later, the holder does not present the original credential. They create a derived proof that reveals only the required attributes, while mathematically binding the hidden ones to the same issuer signature. The verifier checks that proof with the issuer's public key, without learning the concealed values. Decentralized gives credential data shared meaning, not just field names. Claims such as degree, employer, or date of birth can be interpreted consistently across systems. Linked data proofs attach cryptographic proof material to that structured document. Before signing, the data is canonicalized, so everyone signs the same deterministic representation. With BBS Plus, the holder can later derive a presentation that proves selected statements, such as employer or age, without revealing every original claim. In a selective disclosure flow, the verifier starts by asking for exactly what it needs, such as age over 21 or membership status. The wallet selects matching attributes from the full credential without exposing the rest. It then creates a derived proof, usually tied to a challenge so it cannot be replayed. The verifier checks the proof, issuer keys, schema rules, and trust policy, then decides based only on the disclosed claims. Selective disclosure limits what is revealed, but it may still expose exact values, such as age or income. Predicate proofs go one step further by answering only the verifier's question. Are you over 18? Is your membership active? Is income above a threshold? The proof returns yes or no without revealing the underlying data. This reduces privacy risk while still supporting authorization, eligibility, and compliance decisions. Range proofs are useful when the verifier needs a threshold answer instead of the raw value. A user can prove they are 18 or older, that a balance exceeds $1,000, or that a credential was issued within an allowed time window. The trade-off is cost. These proofs are usually heavier than simply revealing one field. A privacy-preserving verifier policy begins with one question. What is the minimum fact needed to decide? If an age threshold is enough, do not request a birth date. From there, define which claims or predicates are acceptable, which issuers and schemas are trusted, how fresh the credential must be, and whether revocation must be checked. The key is traceability. Every requested proof should map to a real business or authorization requirement. Anything broader recreates the surveillance problem these credentials are meant to avoid. Revocation is essential because credentials can expire early, be compromised, or stop reflecting someone's status. The privacy challenge is how that status gets checked. If every presentation phones home to the issuer can learn where and when the holder uses the credential. If revocation lists expose stable identifiers, verifiers can correlate activity as well. Strong designs prove still valid while minimizing tracking, scaling efficiently, and preserving unlinkability. Accumulator-based revocation compresses a large revocation list into a single cryptographic value. The issuer updates that value as credentials are revoked. The holder keeps a witness tied to their credential and uses it to prove mine is not in the revoked set, without exposing the credential identifier. The verifier checks the proof against the published accumulator state. The hard part is operational, keeping witnesses current, scaling updates, and making sure wallets, issuers, and verifiers all support the method. The core lesson is that credentials should prove what matters without exposing everything. Selective disclosure, BBS plus signatures, predicate proofs, and private revocation all support that goal. Next, we move from cryptographic concepts into concrete VC formats, issuer services, wallets, presentations, and verifier flows that can run in real systems.